pounds. Despite Musk's projection during a recent Starbase presentation that Raptor 3 would reach 280 tons, it fell slightly short of 617,000 pounds. This discrepancy indicates that Raptor 3 won't be SpaceX's ultimate version of the engine. So what version will achieve this remarkable feat? Musk provided us with a glimpse of the answer during that presentation.
I think ultimately the booster engines will aim to get the booster engines over 330 tons of thrust, which would mean 10,000 tons of total thrust at liftoff.
Of course, the revelation of a 330-ton engine version marks a significant milestone, surpassing previous discussions of Raptor engine capabilities. Achieving 330 tons of thrust equates to an impressive 727,000 pounds, exceeding Musk's earlier target. This heralds a new pinnacle in thrust for the Raptor engine. While the Raptor engine may not match the individual power of engines like the F1 or RD-180, its synergy with the Super Heavy booster, which can accommodate up to 33 engines, presents a formidable force. Utilizing such engines would generate a staggering 10,890 tons of thrust, or nearly 24 million pounds, establishing the most powerful liftoff thrust in rocketry history, surpassing even the legendary Saturn V rocket. In fact, with the current Raptor 2 version, Starship already boasts the strongest liftoff thrust of over 7,000 tons, double that of the Saturn V's 3,500 tons. Musk's acknowledgement in his tweet underscores a fundamental truth about engine development. Refining factors such as thrust-to-weight ratio, specific impulse, and reliability poses far greater challenges than simply increasing thrust. He astutely points out that rocket engines inherently possess a propensity for catastrophic failure. Improving these crucial parameters is inherently complex, as enhancements in one area can have cascading effects on various other aspects of the engine and rocket system. Achieving optimal balance and performance across these factors is imperative for ensuring the success and safety of space missions. Thus, while increasing thrust is an impressive feat, the true measure of engine excellence lies in achieving advancements in thrust-to-weight, specific impulse, and reliability. Let's go over the intricacies of the thrust-to-weight ratio and specific impulse, two critical factors in rocket engine performance. Firstly, the thrust-to-weight ratio plays a pivotal role in determining a rocket's efficiency. A higher TW ratio signifies greater performance, achieved by either increasing thrust, reducing mass, or a combination of both. Typically, boosting thrust entails adding more components to the engine, which inevitably increases its mass. Balancing increased thrust with minimized mass is a formidable challenge, as reducing mass while maintaining or enhancing thrust is considerably more difficult. Next, let's consider specific impulse, a measure of a rocket engine's efficiency based on the thrust it generates per unit of fuel consumed. Similar to the TW ratio, a higher ISP indicates enhanced engine efficiency and more effective utilization of fuel. This translates to longer mission durations and increased payload capacity, a desirable outcome for every rocket launch organization. Achieving higher ISP necessitates significant changes in materials, fuel composition, engine design, and combustion processes. It's a multifaceted endeavor that requires careful optimization across various parameters to enhance engine performance and efficiency. Reliability stands as the ultimate hallmark of a rocket engine's capability, representing its ability to consistently perform and endure any scenario or environment. It's quantified by the error rate during operation, with 0 errors signifying absolute reliability. Naturally, every aerospace company aspires for the highest level of reliability in their engines. However, achieving this feat is incredibly challenging, as errors can originate from any component within the engine. This sentiment underscores the common refrain that the engine is hard, acknowledging its inherent complexity and the myriad challenges associated with ensuring its reliability. Indeed, the engine remains the most intricate and critical component of any rocket system, requiring meticulous attention to detail and rigorous testing to mitigate potential issues and uphold operational integrity. SpaceX has made significant strides in addressing factors such as the thrust-to-weight ratio and reliability in their Raptor engine development. In terms of the TW ratio, SpaceX has consistently increased thrust across Raptor versions from Raptor 1 to 2 and the latest 3, with thrust values rising from 185 to 230 and 280 respectively. Remarkably, despite these increases in thrust, SpaceX has managed to simplify the design of the Raptor engines. This simplification is evident in the reduction of complex wiring and piping systems, which have been integrated and streamlined in successive versions. For instance, Raptor 3 features significantly fewer intricate details compared to its predecessors, contributing to a notable reduction in engine weight. This optimization has resulted in tangible weight reductions, with Raptor 2 weighing approximately 1.6 tons and Raptor 3 further trimming down to just 1.4. Moving forward, SpaceX is poised to continue optimizing this factor, aiming for even simpler and lighter engine designs in future Raptor iterations. However, despite these advancements, SpaceX has yet to achieve absolute reliability with the Raptor engine. Several challenges have been encountered during test flights, including engine failures shortly after liftoff and issues during separation and landing processes. Despite these setbacks, SpaceX remains at the forefront of the aerospace industry, actively working to enhance the reliability of the Raptor engine.